So I was running a quick filler presentation for you guys, just a brief introduction to OpenGL. It accidentally turned into 100 slides. So this title, yeah, this title is no longer accurate. It's now a joke instead of an actual description. But, so I am Sean Middleditch, DigiPen Senior. I think most people in the room know who I am. So this presentation, again, these slides are slightly out of date, but a history of OpenGL, what exactly it is, what it's for, when you should and should not use it, why you might be interested in it, and then some hints on getting started. This is not going to be a how-to tutorial kind of thing. There's not going to be big blocks of code that you can cut and paste into your own projects. It's just the code that I'm going to have is going to be more things like, here's something you should be aware of that the other existing documentation online almost always never goes over, or the concomitant documentation doesn't explain properly, and I just wanted to make sure you guys had the right information. So first, quick history and description of OpenGL. What OpenGL is. OpenGL is a C API for accessing graphics hardware. It does triangle rendering, has a couple different modes for either fixed or programmable pipelines, which I'll go over a bit later in the presentation what that actually means. It's really just a low-level hardware abstraction. Right? What it's not is anything other than a low-level hardware abstraction. It is not a scene management API. It's not a graphics engine. It doesn't do any advanced features on its own. It literally just renders triangles to the screen and gives you some control on how those triangles are rendered. I see a lot of questions online on certain forums, people asking, how do I do such and such feature with OpenGL, thinking that OpenGL will do this for them. And in most cases, you as the graphics programmer have to figure out how to do these effects. OpenGL just renders triangles, not much else. It certainly doesn't have input physics, anything like that. So there's some reasons why OpenGL is a good choice to use and why you should be aware of it. One thing that I find is that for simple projects, it is actually the easier API to use between Direct3D and OpenGL. And I mean for simple projects. So we're going to go in a bit later about why for more complex projects, it's actually not that great of a choice. But getting up and running in a minimal amount of time is very, very easy to do in OpenGL. That 8-hour game presentation I did a few weeks back, that was all OpenGL, and I got the graphics done in like 20 minutes. There was really nothing to it. Another reason you might want to know OpenGL is that it's the only rendering API available on quite a large number of platforms, including the iOS platform for iPhone, iPad, Android. Technically, Android has another rendering API, but OpenGL is the one to use for actual 3D hardware accelerated stuff. HTML5 uses a form of OpenGL. If you're doing OS 10 or Linux programming, that's all OpenGL only. So if you want to port your game to any of these platforms or develop games for things like the mobile market, which is huge right now, you have to know OpenGL. Direct3D is not going to be the API that you're going to use. Another reason that OpenGL is kind of popular, especially outside of games, is because of the ability to use vendor extensions. So sometimes NVIDIA or AMD will create new features in hardware that Direct3D hasn't exposed yet. And they will initially expose these as experimental extensions in OpenGL that then people can make use of and do some pretty cool stuff. In particular, NVIDIA last year had this really cool 2D rendering accelerated feature they added to their hardware that you can't access through Direct3D. Even if you're using Direct3D's 2D mode called Direct2D, it doesn't actually have the same level of features or performance. The only way to access this capability is through their OpenGL extension. And then one kind of smaller reason is that OpenGL gives you the ability to choose between fixed function or programmable pipelines, whereas the newer APIs generally force programmable pipelines on you. And there's some reasons why you might want to consider not using OpenGL. I know here at DigiPen, there's a lot of people who get very, very loud about why you should not use OpenGL. And they all have very good points. And some of those points are that the API in OpenGL is very old and clunky and nasty. It's bad in a lot of ways. And that when you're doing some more advanced stuff, it can get in your way. And it makes it harder to find out what you did wrong. It is not helpful to you. The Windows drivers are absolutely horrible in a lot of cases. You will run into lots of bugs. If you're doing advanced 3D stuff, you will probably be requiring your users to upgrade to the very latest drivers, whereas in Direct3D, usually the older drivers don't have as many bugs and performance issues. There's also less tools for OpenGL. Direct3D has some really, really great tools for debugging your applications and figuring out what's going on. OpenGL has tools, but they're not as good. And then there's also no Xbox 360 support. There's very, very limited PS3 Wii support. And you're going to require extra drivers even on Windows. The point being is that if you are targeting the main PC gaming platform or the Xbox as a gaming platform, OpenGL does not help you that much. For Xbox, not at all, actually. So if you're doing just a PC game, like most of your DigiPen games, portability is not something that you should worry about, and it is not a reason to pick OpenGL, because you're not going to be porting your games to a lot of platforms, most likely. All right, so OpenGL version 1.0 came out in 1992, which was a really long time ago. We'll go over, it's C89 came out in, I think, rather obviously, 1989, and C++ 98, which was the version of C++ that most of you will be learning or have learned and are familiar with, has most of the features that you would associate as being C++ features. That came out years after OpenGL first came out. And OpenGL was originally used internally and developed before C89. So it does not take into account modern programming practices, which is one of the reasons why the API can feel so clunky and old at times. I'd like to break down OpenGL into 5 major generations, different versions of OpenGL, roughly speaking. There's the original OpenGL 1, which was an old form fixed function designed for SGI's hardware, SGI being the company that designed OpenGL. They were basically the people who made graphics cards back before there was this huge market for consumer graphics at all. They were all pretty much workstation for CAD and imaging and professional kind of graphics stuff. So it was basically a raw wrapper on the capabilities of their hardware. Their hardware was not programmable. Shaders had not been, they had not become a thing yet at all whatsoever. OpenGL 2 is what added the first programmable pipeline support. That means it added shaders, and you can start doing cool effects besides just rendering textured triangles, essentially. OpenGL 3 and 4 are the modern versions of OpenGL. I kind of lumped them together because really all 4 did was just add more features to 3. It didn't fundamentally change the way you do graphics programming with OpenGL. One thing, however, that's really worth pointing out with OpenGL 3 and 4 is that they added what was called core profile, which is a way for them to basically turn off and disable old deprecated features that you're not supposed to use anymore. So programming in OpenGL and core profile can feel a lot different than programming older OpenGL. Normally this won't matter. Every driver out there has compatibility mode turned on by default, unless you're programming for OS X. OS X, in order to use OpenGL 3 or 4 and get the OpenGL 3 features, you have to use core profile mode, which means you have to not use any of the deprecated features from 1 and 2. I'll go over that a little bit more later here. There's also then the OpenGL ES, which is the mobile variant. ES stands for embedded system, if I recall correctly. So OpenGL ES1 was for it's a fixed function on mobile devices. And then OpenGL ES2 was programmable pipelines on mobile devices. So things like the iPhone or Android are all using OpenGL ES2. So just quick slides here if you want to look back on what just went over. Oh, yeah, it's actually another interesting fact. With OpenGL 3, there's this kind of fun historical quirk called the Long's Peak controversy. What happened is the guys in charge of OpenGL promised that they were going to make this really new, awesome, clean, object-oriented, API that would just be so cool and better than anything you'd ever seen before. And everyone was really excited. They had samples out. It looked really good. And then they went media blackout for like 6 to 9 months, and nobody heard anything out of them. They didn't post the forums. They didn't respond to any inquiries at all. It was like they just disappeared off the face of the earth. And then all of a sudden, one day, they just kind of popped out of nowhere and said, here's OpenGL 3. And people were really upset because it turns out that all the cool stuff they were talking about, they threw away. They just added a few features to the old OpenGL 2 API. They didn't even add all the features people wanted. Direct3D 10 was already out. Direct3D 10 added geometry shaders. But OpenGL 3.0 didn't support geometry shaders. It actually, I don't think those came until 3.1 or 3.2. So people were really upset that they waited all this time, this cool API never came out, and then the features were just kind of lacking. This is when OpenGL really started lagging behind Direct3D for a while. It's just really interesting. You'll see, if you get online and you read about the history of OpenGL, this comes up a lot. So it's a little fun historical fact. Yeah. All right, so looking forward about what might happen with OpenGL in the future here. OpenGL 5 is rumored to maybe be coming out in a year. We'll see. I mean, rumors are just not reliable generally. Direct state access is something people are asking for a lot. That essentially means that some of the functions we'll go over later, the bind functions, which I'll go over, would go away, which would be amazing, because those are like the worst part of OpenGL. There's also a strong indication that OpenGL ES3 will be coming out soon. That will probably just add newer features to the mobile platform. A lot of newer mobile GPUs have geometry shader support and other features that aren't built into OpenGL ES2, so they'll just be adding those. All right, so I went over, used that term fixed function versus programmable pipeline. So I'm going to go over quickly what that's all about. Essentially, that comes down to shaders. So fixed function means that the mathematics for how you do lighting and other parts of the 3D rendering are built into the hardware. It's fixed and not changeable. So this usually, this would mean the lighting model, how fog works, bits of texturing. So essentially, if you have a model and you apply your textures to it and your colors to it, it's just going to come out looking one particular way and you have no way of customizing it. So it was very limited. There were not a lot of really cool features like we see in today's games because you couldn't override the pre-designed mathematics of the math. Whereas the programmable pipeline now allowed people to replace parts of the pipeline with their own user-written code. The very early versions of this was basically just little bits of the lighting equation. This was enough to do things like cell shading. Right? As soon as you can replace just the base lighting equation, you can do cell shading, which is a cool feature. And it looks awesome. Sure, you've all seen games that are using that feature to neat effect. That wasn't possible with a fixed function pipeline. And then the modern programmable pipeline allows you to replace almost everything in the graphics card with your own custom code. And you can really customize how things work and do a lot of cool effects. There are some bits that are still fixed function. I hear people every now and again talk that modern graphics is all programmable and you can replace everything. Just to be pedantic, that's not quite true. There are certain things that are still baked into the hardware and you cannot replace. The triangle rasterizer, for anyone who's taken CS250 or that class, essentially that loop where you render your triangles, that's baked into the hardware. There's no way to replace that, and that's a speed thing, really. Texture filtering, again, it's a speed thing, so the way it deals with smaller textures and zooms them in or out, that's baked in for speed. There's a couple other optimization things. Early depth testing, by definition, it is a feature that avoids running your code so that it goes faster. So having to write code for that would not really help much. Blending and a few other bits are just kind of just baked in there. A few of these might get replaced. There's rumors that blending might be user replaceable in the future, but we'll see. So there are some reasons to still use fixed function pipelines today. One of them is that it's just easier. You don't have to write a shader. If you don't need to customize any part of the pipeline, why spend a bunch of time writing code to write stuff that's standard in older versions of OpenGL? You can just save a lot of time if you just need like basic sprites in a 2D game. There's no reason to worry about shaders unless you're going to get into effects, essentially. And it's also cheaper to make hardware, so there's still a lot of hardware produced today that does not have shader support. The Wii, I believe, does not have shaders. The 3DS, I know, doesn't have shaders. A lot of phones that have 3D capabilities but are not our modern smartphones, again, do not have shader capabilities built in. So just if you're thinking about using fixed function in OpenGL, that means you're going to be using OpenGL 1 or OpenGL ES1. You can also use it in OpenGL 2. You can use it in 3 or 4, but remember that if you're in core profile mode, they deprecated things. And one of the things that they deprecated was fixed function. So if you want to use OpenGL 3 features on OS 10, you have to make sure all of your code is ready to use only programmable pipelines. You can't mix and match like you can on Windows or Linux or any other platform that uses OpenGL. And just for comparison, Direct3D 7 was the last version of Direct3D that had only fixed function. 8 is when they started adding shader support to Direct3D. And then if you want to do programmable pipelines, that means you're going to be using OpenGL 2, which is available everywhere. If you're using OpenGL 3, again, you have to use programmable pipeline. And if you're using, again, for comparison, in Direct3D 10 and 11 both require shaders. There's also a couple different versions of shaders you run into. One of the older ones that you don't see much anymore is what they call the ARB assembly language. ARB stands for Architecture Review Board, and it was a group that basically managed OpenGL back in the past. But it was similar to D3D assembly shaders. If you ever see those, you might see them in some debugging tools. Again, you won't write these anymore, but you might see them if you're like looking at older programs or if you're using certain tools that kind of generate compatible code for older hardware. Then there's also the OpenGL shading language. Now, if you're writing actual shaders, this is generally what you're going to be writing your shaders in. It's a C-like language. I mean, it looks very, very similar to C. It's actually designed intentionally to be a lot like C. It's very similar in scope to HLSL, although HLSL has some features that GLSL does not have. And one thing that's kind of notable about the shading language is that they actually make a new version of the shading language for every minor release of OpenGL, and they are not shy about breaking backwards compatibility in the shading language, unlike their API where they almost never do it. So you have to be aware of the fact that you can see a shader that might be using some code that if you try to copy it into another shader using modern features, the code won't work together. You're going to have to update some of that code to work with the newer syntax. There's another kind of cool thing out there called NVIDIA CG. This is it's a custom shading language, but it's basically HLSL with a few extensions to it. The neat thing about CG is you can run your shader through CG and it will generate now shaders in other languages for you. So you can write one shader in CG and it can spit out the GLSL version, the HLSL version, and it also spit out those old ARB programs. So if you wanted to run on old hardware that doesn't support the modern version of GLSL, you can just write one shader and target all these different APIs and different versions of hardware. It's pretty handy. One problem is that it does not currently support OpenGL ES, which is kind of the important version of OpenGL, since that's what all the mobile phones run and that's where all the action is with OpenGL these days. So it's an unfortunate thing. I'm assuming that NVIDIA is going to be updating CG to handle OpenGL ES soon, though, since NVIDIA is getting to be a pretty big player in the mobile phone sector. So I'm going to give you some hints about how to get started with OpenGL. So if you've never done any graphics programming at all and you're kind of thinking, well, how do I even get something on the screen? These slides will help you. And if you have gotten stuff on the screen, then now's a good time to take a nap. So quick warning, this is OpenGL 1. Right? This is not this is the 1992 version of OpenGL. These functions we're going to be going over here. This API is great for getting up and running very quickly. It takes very little code to get something on screen. However, it is considered slow and old and nasty, and some people get very angry if you're using it. Some people get very emotional about code. I would not. Just be prepared to that fact. If you show them some code you wrote like this, they might say mean things. They're just being mean to be mean. This is a perfectly good way to write code if you don't need any of the advanced features. So the first thing you have to do whenever you're programming OpenGL is create what's called a context. This is your connection to the hardware itself. This is the equivalent of a Direct3D device, essentially. Now there's a couple different ways to create contexts. I would actually recommend using a wrapper library. These libraries kind of abstract bits of OpenGL from you, including the OS integration part. So there's libraries like GLUT, GLFW, SFML, and SDL. GLUT is by far the easiest in my opinion. It takes a couple function calls and you've got a window open, you've got mouse input, keyboard input, all the basic stuff you need to actually have an app up and running. It's just there, it works for you in just a few function calls. SDL is really popular. There have been big commercial AAA games that have shipped on top of SDL, so it certainly works quite well. And then SFML is many times claimed to be the cleanest of the current toolkits because it's object-oriented. So a lot of people feel a lot more comfortable having a C++ object-oriented API. But essentially, if you use one of these wrappers, they will deal with creating a device for you. So if you use GLUT, when you say create window, it will create the OpenGL context and you don't have to do any extra work at all, which is why I recommend going that route. All right. So now once you have your context created, you have to create what's called a projection matrix. The projection matrix is a mathematical entity that basically takes points in 3D or 2D and maps them onto your screen. So there's mathematics behind that, which you guys will all learn in CS 250 if you haven't had that yet. And if you don't want to go through that math, there's functions built into GL that will generate the matrices for you. And I would just recommend using those to get up and running. So a 3D perspective matrix. If you want to make a 3D game where objects have depth and things that are farther away get smaller, all that, you would use lines of code pretty much like this to get things set up. So the way this works is OpenGL it works as a state machine, which I'm going to get to in just a bit. But you have to tell it what matrix you want to modify. So we want to set up the projection matrix. So we say GL matrix mode, GL projection. So now any other matrix functions we call will modify the projection matrix. There's a few other matrices in OpenGL. So you got to make sure you're telling it to modify the right one. GL load identity loads an identity matrix into the current matrix stack. An identity matrix is something if you multiply, you get the same thing back. I'll go over why you always want to call this at this point. Then you call glue perspective. So it's GLU, because this is part of the utility library for GL. But GLU perspective, you give it the field of view you want, your aspect ratio, near and far values, like 0.1 and 1,000 are pretty common values there. And at this point, you now have a 3D projection matrix, and you can start running 3D objects and have a 3D scene. And there's no extra work to it at this point. If you want to do 2D work or a 3D orthographic projection, this is what you do normally use for 2D. It's almost the exact same code, except now we call GL ortho 2D. You give it the width and the height in that kind of weird order there. And now you're set up, you now can render to your screen in 2D. That's all you got to do, and you're up and running. So I mentioned before that everything works in a matrix stack. So what this means, again, is when you call a function to modify a matrix, it modifies a matrix in essentially a hidden global variable. So you say GL matrix mode, tell it which model or which matrix it is you want to modify. In this case, we're modifying the model view matrix, which is the matrix you use to get an object onto your screen. Then we have other functions like GL translate, GL rotate, GL scale. These will move the matrix's coordinates around so that the object will, say, move in a different spot or be spun or at different sizes. So the way these work is when you call, say, GL translate, it takes the existing matrix on the top of the stack and modifies it by that translation. And translation means moving. This is the reason we did that GL identity at first, because if there's other matrices, if there's another value on the matrix stack and you just call GL translate, it's not going to replace it, it's going to modify it. So you call GL load identity to get back to a default starting position. So another thing you can do is use GL push matrix and GL pop matrix. This is a handy feature, particularly with model view matrices, if you have multi-part models, like in your CS classes, your graphics classes, the tank example is used a lot. So you have this tank body, and then it has wheels, and there's a turret on the tank. So instead of having to figure out how to independently position all these different little models so that they happen to just be aligned correctly, you can say, where's the matrix for where the tank is in the world? And now we're going to push that matrix and start modifying that one to say, well, now I want to take whatever that position of the base tank was, but now move over and rotate to put this wheel in place. But now we're done with that wheel, so we call pop matrix, and that resets us back to the base tank matrix. Now we can do another matrix modification to get to the other wheel, pop that, do another push. It's convenience. Again, this is not the way you would write like a real high-speed AAA engine, but getting up and running quickly, or for small indie games, this just saves a lot of time. All right, so now that we've got a matrix in place, we got those 3 lines of code, and we got the window open from glut to SDL, we want to actually get a triangle on the screen. Again, this is really easy with OpenGL 1. We had to call GL begin, which says we want to start rendering. We also tell it what we're going to be rendering. There's a few options in OpenGL. Triangles is the common one if you're rendering a 3D mesh. You then give it the vertices of your object. So a triangle, you need 3 vertices. I specify 3 points in 3D space. I call GL end, which says I'm done drawing, and at this point there will be a triangle on the screen. That is really all there is to it. If you want to render points or lines, you just change GL triangles to GL points or GL lines, give it the correct number of vertices. It's worth noting that if you want to render multiple objects, like say you want to render 2 triangles, get really fancy with your graphics, you just put 6 entries here instead of 3. You can put as many in there as you want as long as you have the right multiple for whatever you're rendering. Triangles needs 3, so just always call 3. And obviously you can have this all data driven. This can be a loop or whatever you want inside inside the GL begin, GL end to read your data and render your models. However, it can be convenient for testing when you're just getting running, just hard code some points in there. Again, just get up and running, get something on the screen, you can factor that out and get it into an actual nice data-driven format after you have the basics already working. So this is just going over how everything works. I'm pretty sure I just said, oh yeah, the big thing. A lot of OpenGL functions cannot be called inside of GL begin and GL end. So once you call GL begin, you should pretty much do nothing other than call the drawing functions, the GL vertex and some of the other ones we'll go over in a bit, and then call GL end. Any other functions, like when we talk about texture loading and things like that, it can be illegal sometimes to call those inside of the GL begin, GL end. All right, so we've got vertices and we've got a triangle on the screen, but we're going to at this point be dealing with a white triangle on a black background, and that's really boring. We like color. So one of the way we do this is specifying additional vertex attributes, or an attribute would be things like the color of a vertex, or when we get to texturing, telling it what part of the texture is applied to this vertex, so we can actually arrange how the texture is applied to our triangles. Then you also need normals as soon as you start doing any kind of 3D lighting. So the way we do this is just by calling these functions, GL color, GL text chord, GL normal. I think these are the ones built into GL1. There might be a couple other weirder ones that you don't use much, but those are the big 3. So those functions, you notice when I called GL vertex, it had 3F at the end. So just so you know what that means, it is essentially the number of components and the type of components. So when I call GL vertex 3F to make those points, I was giving it 3D coordinates. So there was three components, and I was passing in floating point numbers. So there were 3 floats. Then we do colors. For example, you might be specifying color with 4 unsigned bytes. You'd call GL color 4UB. This is just because C does not have method overloading, so they had to have ways of identifying like the 20 bajillion different ways you could call these functions, because they support a lot of different formats. Yes, just get back to these real quick. One of the things to know about how these work, when you call GL color GL text chord, it doesn't actually do anything. All it's doing when you call GL color, it says the current color that I will draw with the next time you call GL vertex is now this color. So inside of your loop, when you've got this guy here, if you want to add color, you set color before you call GL vertex, not after. GL vertex actually sets the vertex for rendering using whatever the current rendering state is. So you could call GL color here and set it to red, and then call GL vertex 3 times, and you get 3 red vertices, and then your whole triangle's red. Or if you want to change each vertex, you have like a nice multicolored triangle, you just change for each GL vertex call. Another nice thing that's really nice to do is get an actual texture onto our triangles, or quads in the case of sprites, which is what most of you are going to be dealing with in your sophomore games, or possibly even your junior games. A lot of indie games, 2D's pretty popular. Textures are nice. There's unfortunately one problem with my theory that OpenGL 1 is very easy to use, and that is the fact that OpenGL does not give you any way of loading a texture. Actually getting it off disk and decoded into memory from whatever file format you're using, it's not built into OpenGL. It's not part of the OpenGL utility library. The utility library actually just has math functions and nothing else. Luckily, those wrapper libraries that I recommended to use for getting your window and your context created, those generally have these features built in. So SDL, GLFW, SFML, they all have functions for loading textures. Some of them will integrate directly into OpenGL, like GLFW. Its texture loading is going to get rid of the next 2 slides. You don't have to do the extra work I'm about to tell you need to do. So some of these can be pretty nice. You can also use another library for loading things. You could use libping directly. Right, yeah. So I'm going to go over a bit about why OpenGL's API is considered bad, but you do not understand a bad API until you've seen libping. It is disgusting. So don't use libping. If you hear people say that's the correct way to do things, they're wrong. Don't use it. All right, so in order to create a texture, you have to create an object. Now, of course, this is a C API. You don't have an actual struct or a class, with virtual methods or anything like that. And because this is an old, clunky C API, they actually just use integer IDs for everything. They're called names in OpenGL. So if you read OpenGL documentation, they say the name of an object. They mean the integer value they have assigned to that object. So in order to create objects in OpenGL, you have functions of the form glgen and then the type of object you're generating. So if we want to generate a texture, we got to create an integer. GLint is just OpenGL's int type def. It's just an int. They did this back in the day. There was concern that maybe on some platforms ints might be weird sizes, like the standard int might only be 16 bits, and they wanted to make sure that their int was 32 bits or something. It's kind of a historical artifact. This literally means the exact same thing as int. But yeah, so we call glgen textures, and then we give it this weird little format here. So the reason that they do this is they thought it'd be a great idea to let you generate multiple objects at the same time. Because if you're going to need 10 textures, why make 10 calls to create textures? In reality, you only create one thing at a time. Even if you're creating 10 textures, you're going to have everything wrapped and abstracted. Once you get nice form, you're not going to be calling glgen textures 10. You're just going to be doing it one at a time, so it's just corrupt. So just always call oth1 and then pass it the address of the variable you want to put the name into. So when you've created this object, it exists, but there's no way to modify it. So I mentioned before about direct state access. This is where the bind functions come in. So remember when we went over GL color, I said it set state that then GL vertex used. So you didn't actually modify anything. You just said OpenGL, the next function I call, use this data. Everything in OpenGL works that way. Everything. It's really annoying. So you have, after you've created your texture, you have to say, well, all the texture functions I'm going to call to say upload data into the texture or set parameters in the texture, you have to tell OpenGL which texture you want to use using another function call. That's what bind does. So in this case, we're saying, hey GL, I want you to take that texture I just created and bind it to my texture 2D slot. So yeah, also kind of weird. OpenGL has multiple slots. There are more than one type of texture slot. You can have something bound to texture 2D and texture 3D at the same time. I cannot imagine why they thought that was useful. But yeah, so generally, most textures you're dealing with are 2D, so you're just going to see texture 2D all over the place. That's just what that's for. But you'll see that come up on the next slide here. So you notice this, in order to get data into the texture, we call it GL text image 2D. But because it wasn't apparent to OpenGL that GL text image 2D modifies the 2D texture, we have to tell it that we're modifying the 2D texture. And then there's all these parameters here. So the width and height would be the width and height of your image in pixels. Pointer to pixel buffer is going to be an unpacked, uncompressed, just raw memory of this data. So for example, if you're trying to load a ping image is not raw data, it's compressed and all that kind of stuff. You cannot just open a ping, read it into memory, and pass it this function. That does not work. You have to have another library that knows how to decode ping and turn it into that raw buffer of memory that you pass to this function. And just for a couple of these other options here, this function is really poorly documented, poorly understood. So the 7th parameter and the 8th parameter. So that's the GL RGBA on the end of the second line and the GL unsigned byte here. That is telling it the layout of the stuff in memory. So if you have an RGBA texture, which is kind of your standard memory layout, GL RGBA. And then if it's a single byte per component, so you got 8 bits for red, 8 bits for green, and so on, that's what this means. So now the 3rd parameter, which is the GL RGB8, if you look at documentation, it will lie to you about what this does. In old versions of OpenGL, this was supposed to be the number of components. So we have an RGBA texture, so that's 4 components. So you put 4 here. Now there's a problem with this, is that you could say we have 4 components and they're in the RGBA order and they're unsigned bytes. But some formats, that's not enough information. For 16-bit textures, for instance, 3 does not divide into 16. So one of your components gets more bits. And the question now is like, which bit where does it go? So this right here, for example. Once I create a texture, I can replace the data in that texture. So I've allocated memory on the graphics card for a 64 by 64 texture, and I can replace that value with any pixels I have. So yeah, this is one of the examples of modifying a texture. There's a few other functions for modifying textures, things like wrap mode. If you say, I've got this texture and I want to put it on a wider, the way you specify the texture coordinates, if instead of giving it 0 to 1, you give it to 0 to 2, for instance, with 0 being all the way on the left and 1 being all the way on the right, what does it do if it goes past 1? That's an option you set on the texture. So there's other functions you can call to modify that kind of stuff. So you have to have the GL texture bound in order to do that. Because yeah, you notice in GL text image, I never pass it that integer for the name of the texture I created. It has to be bound to, with that other function call for this to even know which texture it's modifying. But yeah, so yeah, it turns out that knowing its 4 components and what order they're in, there just wasn't enough information. So OpenGL guys, they don't like adding new functions if they can find a clunky way to reuse an existing function. So they repurposed this because, hey, we know it's 4 components. This is RGBA over there. It's 4 components. Why specify that twice? So now you can right here specify that it is an RGBA 8 image. So that means that it's got RGBA and it's got 8 bits per component. You might also see things like RGB 656, I think, or 565, one of those, for a 16-bit component, or a 16-bit color where it says like green has 6 bits and the other 2 have 5 bits. So they give a lot more flexibility. Of course, these other parameters are still here, and a lot of drivers will error if they're not matching this. So anytime you want to use different texture formats, you're going to have to basically give it the same information 3 times. Yeah, what can you do? But I mean, you write this once, you don't have to worry about it again. So now you've got this texture loaded, but if you actually want to draw it onto your, with your polygons. So first you have to do is you have to tell the fixed function mode you want to use texturing. Because again, you're not running shaders, you're not running code. It's kind of got these features built in. Most of them are off by default. GL enable, GL texture 2D is just saying use texturing. That's all it does. And then there's the GL text chord 2F. So back again in our GL begin, GL end, GL vertex, and color we were talking about. This is just telling it, for each vertex, which point in the texture you're using. So if you have a quad that's got 4 points and you want to map the 4 points of your texture to that quad, you'd call GL text chord once for each vertex with 0, 0, 1, 1, and the various combinations there to get everything drawn on screen. So it's not a whole lot to that. It can sometimes take a little while just to get your head wrapped around texture coordinates if you haven't used them before. It also doesn't help that OpenGL's texture coordinates are upside down from Direct3D. and there's no way to swap either of them. Like Direct3D does it its way, OpenGL does it its way. So if you're getting online and looking at any samples that have textures, and it's maybe a Direct3D sample that you're trying to port over, you might get things upside down. So just be aware you have to invert your texture coordinates. And then lastly, if you want to turn off your texture, so let's say your game has maybe some solid color stuff as well as textured stuff, and you want to now stop drawing whatever texture you have, you unbind the texture. Because when it draws with whatever texture is bound. You can go GL bind texture with 0 as the integer name. That just means bind nothing. So now no texture is used. Incidentally, now any of those functions like GL text image 2D you cannot call because they will modify nothing. So if you want to start using that texture again, you got to reset it. And then if you're all done with your texture and you just want to throw it away, the pattern in GL is GL delete whatever, and then that same 1 and the address thing. So I mean, usually you wouldn't even need to worry about this too much, but when your game starts up, maybe you want to delete your DigiPen logo screen because you're not going to use it after the game starts, so that's just your loading screen. So you can do that. All right, now we've got something drawing in the screen, but we don't have double buffering, and modern rendering systems generally require double buffering to some degree, just because of the way graphics kind of work in the modern operating system world. So you now have to flip buffers. Double buffering means that whatever you're drawing draws to an off-screen hidden image, so you can't see it being drawn, and then it gets flipped to the front. If you don't have double buffering, what can happen is you can actually watch the scene as it's getting drawn out, if you had a slow enough computer or fast enough eyeballs. But again, modern operating systems and graphics stacks can't even really operate outside of double buffering mode just by the way things work. So double buffering is there. Interestingly, the buffering command is not built into OpenGL. And I'm not going to make fun of OpenGL here because it's the exact same way in Direct3D. This is by design. Direct3D has what's called DXGI, which is the DirectX graphics interface, something like that, I think. Essentially, it's another part of the DirectX suite that's responsible for flipping buffers and creating windows. So OpenGL also has a separate companion library for that. Now, unfortunately, OpenGL has a lot of different companion libraries because they're all OS specific, because their whole purpose is kind of binding OpenGL to whatever the operating system does. So on Windows, there's WGL. On Apple computers, there's AGL. Linux uses GLX. EGL is used mostly on mobile devices, although there's some talk of bringing that to the desktop, so we only have one of these something GLs to use everywhere, which will be really nice. And then SDL and those other wrappers like Glut I went over, those have wrappers built in so that they just work in whatever operating system. So the result of that is that I can't actually tell you what function to call to swap buffers. It's going to depend on what wrapper library you're using. If you decide to go the raw WGL route, which again is the most painful because you got to create your own context if you do that, but it's WGL swap buffers. If you're using SDL, you're just going to look at the documentation, whatever library you use, and get that sorted out. Some of them actually don't need this. I think Glut does not require it. It might. But I believe just the way it works, it automatically does a swap buffer at the end of the loop. Lastly, you're going to want to clear the screen. Otherwise, you're going to draw your triangle, and then you're going to move it next scene, and you're going to see the triangle you drew before, and now the second triangle you just drew on top of it, and that's not what you want. This is really easy. You just call GL clear, and you give it color buffer bit, which just means clear colors. Then if you want to change the color it clears, you can do GL clear color. Note it does not take a 4F at the end or anything like that. There's only one version of clear color. You always got to give it 4 floats, with 0 being off, 1 being on. So if you want full red, you just set the first one to 1.0. Really not much to that. A couple other features you may or may not want to use. One is depth testing. If you're doing a 3D game, so using a perspective projection matrix, you really want depth testing. Rendering without depth testing requires you to sort objects. Basically, the idea here is if you've got 2 objects where one's in front of each other, or one's in front of the other one, which one do you draw first? And if you draw, say, this guy first, and then you draw this guy, you're just going to draw all of its color on top of this one, and you're like seeing through objects, and it looks really bad, and you can't tell what's going on, and it just doesn't work. So depth testing is a technique to fix that. I think you write depth testing in your CS250 assignments, so that'll be pretty obvious what that actually is doing and how it works. For 2D, you don't necessarily need it. It's actually a lot easier to sort things in 2D, particularly because you don't have things at angles, and you don't have to worry about overlapping weird angles. And also just usually when you're running or doing a 2D game, you have this built-in sense of a layer that you can very easily used to sort your objects without having to do extra work. So if you're doing a 2D game, you probably don't need to worry about depth testing. But if you want to use depth testing, you tell GL you want to enable it. So they say GL enable GL depth test. And then the depth testing requires a buffer that also has to be cleared. So when you call your GL clear function, just toss in a bitwise OR with your color buffer bit and depth buffer bit. And that's why it ends in bit, because they can be ORed together as a bit mask. All right, so if you're running 2D sprites, there's really not a whole lot to it. The easiest way is when you call GL begin, you're going to use what's quad. So that's just 4 points instead of 3. Just be careful, your quad all has to lie on a plane, otherwise it's not obvious what it'll do. I think it's technically undefined. Yeah, other than that, it's the exact same as rendering anything else with OpenGL. There's no extra work or anything special about rendering with sprites. If you're going to do transparency in sprites, it's actually pretty critical. It's difficult to have a good looking 2D unit without some transparency. First, I'm going to just be a little bit of a pedantic programmer here. If it's transparent, it is 100% see-through. If it is kind of see-through, it's translucent. And if you can't see through it at all, it is opaque. And I'm actually being pedantic for a reason here, because there are advantages to only doing opaque and transparent. It is very fast to do opaque and transparent, but translucent, now it gets really hard. Now it actually has to blend colors, and this requires things to be ordered even if you have depth testing. So you really, really want to avoid translucency as much as you possibly can and stick to either 100% see-through pixels or not at all see-through pixels. So in order to get depth testing work, you usually have to turn on alpha test. And then there's this function, you just call that to basically say we want only the transparent objects to work. There's not really much to it. If you're going to be doing things with translucency, you're going to want to tweak these values a bit. Yeah, otherwise there's not much to it. All right, so that was OpenGL 1. I'm going to go over some of the techniques we use in modern OpenGL programming so that after you guys get up and running, you decide you want to do some fancy effects, you can actually get those written. Or if you just want to get rid of the OpenGL 1 code so people don't make fun of you, you can do some stuff here too. All right, so the first thing you want to be aware of is the use of a vertex buffer. All right, so the point of a vertex buffer is that GL begin and GL end are kind of slow. And if you think about it, it's not surprising. Like if you want to draw, 1,000 triangles, you got to call GL vertex for each vertex of each triangle. So that's what, 3,000 calls for 1,000 triangles? It's a lot of function calls, right? It's just the way that it's kind of designed. It's not super quick. And if you want to keep redrawing things over and over, you have a single model that's not changing, and you got to sit here and every frame redraw the same thing. That's not good. We have all this memory on GPUs today. You should just be able to upload your model once and keep it there. So vertex buffers let you do that. So just a quick review of the functions you're going to want to use them. To create a buffer, delete a buffer, you get GL gen buffers, delete buffers, just like we had GL gen textures. GL buffer data is a function that just takes a pointer, uploads data into the buffer. And then there's GL vertex attribute pointers, how you set up, you tell OpenGL what data is in the buffer, and draw arrays is how you actually draw with it. I'm not, again, going to go over code samples or tutorials or anything like that, but if you are curious, these are the things you want to Google along with the vertex buffer. The other thing that you're probably all really interested in is shaders, because shaders is, that's what makes graphics awesome. Nitronic Rush without shaders wouldn't, who would care about that, right? That's just a car racing around. It's the pretty lights that make Nitronic Rush so awesome. So shaders, once you start getting to shaders, you're just going to be writing GLSL. There's really not a whole lot of actual OpenGL programming to shaders. It's all in the shading language itself. How to write shaders, how to debug shaders, all that is a lecture or 3 all on its own, so I'm not going to get into that here, because remember, this is a brief lecture. All right, the functions you're going to want to look up are create program, create shader. That breaks the OpenGL tradition. It's not GL gen programs, noticed. They started realizing that was a dumb way to do things, and so now we've got 2 patterns here. I'm going to go over a little bit of just what this terminology means. So in OpenGL, shaders are broken into 2 parts. They have a shader program and then the shader object. A program is the thing that you actually give to the hardware, whereas a shader is a single stage. So you hear vertex shader versus fragment shader, for instance. Shader is the ones that specialize to each of those, but you have to combine them into a single program. There's what's called separable shaders. This is a feature they added finally in OpenGL 4, when that makes it work more like Direct3D does and more like the actual hardware works. This idea of a program object was something when they designed OpenGL 2, the company 3D Labs came around and said, hey, we want to really update OpenGL, and we designed this awesome shading language, and just because we're worried about where the future might lie, we thought about where the future is going to go with hardware, and we've got this great design. And it turned out that their guesses as to where the future of graphics hardware were going to go were utterly and completely wrong in a lot of cases, and we get program objects. All right. So in order to use your shader, if you want a standard vertex shader and fragment shader like you need for most techniques, you need to create a single program and then 2 shader objects. So to create these objects, it's pretty simple. You got integer identifiers, integer names for your objects. GL create program, you see it just returns the value instead of doing that 1 in the address of thing. There's vertex shader, same thing. And then the vertex shader and fragment shader are creating the actual shader objects. Once you've done that, you now need to load the source code you wrote for your shader. Once again, OpenGL does not give you a function for doing this, so you got to do it yourself. Thankfully, reading a text file off disk is very easy. If you can't do that, you're in the wrong room. So you call this function here, which in case the simplification where they made it easier to create the shader, if that started seeming like too much of a good thing, they went back to an awkward interface for actually setting the source for the shader. Yeah, just you give it the direct object you're modifying, so that's what direct state access. That's what that means. We don't have to call GL bind shader before we can modify it. And what is bouncing? That's weird. Oh, nice. That's high quality stuff. All right. Yeah, you just give it the string. So vertex source would be a string. Again, GL char is the same as char, but you get this weird cast just because the way it's specified internally. And then the length of your string, and you now have source code to your shader loaded in to your driver. At this point, you now compile the shader. Compiling a shader doesn't actually do much. You would think it would compile a shader. It doesn't. This goes back again to they thought there'd be this cool thing with like shaders and programs as these like separate parts that didn't actually work out. So compile shader probably doesn't even do much in most drivers. I think it'll do like some syntax validation, but it doesn't do any of the actual work. But you should check for errors anyway. This is one of the things I just wanted to give you guys code. I know I said there would not be code. I lied. This right here, just cut and paste this. This works. It is hard to find this sample online. A lot of people don't have it, and their shaders don't compile, and then they have no idea why. This right here will print out the exact reason your shader didn't compile. Again, though, compiling doesn't actually do much. So now we get to using that program object we created. We link shaders together into a program. So they thought this would be just like C, where you compile each individual C file and you get an obj file, and you link it together to get your exe. That's exactly how the hardware and graphics cards work. That's what they thought. So you attach a shader to the program, and just a couple of easy, nice function calls there. And then you call link program. Link program obviously compiles it. And then you check for errors, and if you had any actual errors in your code, this is going to be where all the stuff gets spit out. So if you decide to be lazy and you only want to cut and paste one slide out of my lecture, do this one, not the previous one. All right, then to actually use the program, again, instead of having the same consistent bind terminology that you're used to, they now call it use program. And then if you want to turn off your shader, because again, maybe you're only using shaders sometimes, some of your objects don't need the shader, you just call it with 0, and you are done with the program. And that's pretty much it there. So vertex attributes. There are a couple different versions of how to upload vertex attributes into the graphics hardware. So there's the one we went over earlier, which is where you call GL color and then GL vertex. There's a few others. So the first style is those built-in functions. GL interestingly had a way to do things with pointers without calling GL begin. So like if you have an array, like you're gonna have 10 vertices, so you have an array of 10 colors, you could set it with GL color pointer. So yeah, that's the old way of doing attributes. These functions have been repurposed now to be used with the shader pipeline. So in a basic older shader, you can still use all of these functions, and then for custom attributes, which some effects you need to pass extra data besides just color and normal. Vertex attribute pointer is the way you define those for OpenGL's usage. In older versions of OpenGL, OpenGL 2, and compatibility mode, you can also just use GL color pointer, for instance. but in core profile or OpenGL ES2, those are all gone. You have to use vertex attribute pointer for everything. But kind of annoyingly, these functions existed before those vertex buffer objects we went over. So vertex buffer objects exist on the GPU. They're memory you allocate in the GPU itself. Whereas we just have an array in your program that's allocated on the CPU in your program. So they had these functions for arrays, and then they decided when they added vertex buffers that we're just going to use the same functions because we can find ways of abusing it to do that. So when you look at the examples, when you guys find code samples for vertex buffers, because I know you're all going to do that, you're going to find that the calls to these functions get really weird. So instead of passing it the pointer to your array, they took the field that's the pointer, and that is now the offset into your vertex buffer. So essentially, if you want something to say 4 bytes in your buffer, you cast that into a void pointer and pass it to the pointer field. It looks really weird and it's odd, and if you're wondering why you have to do that, again, historical reuse of function. And all right, so this is another thing I kind of really wanted to point out with this lecture. If you get online and you're looking at how to specify vertex attributes, you're going to see references to GL get attribute location. All right. You call that after you've linked the program, and let's say you've got a custom field, or let's just say you're using color because you want to do things a modern way, so you always specify color manually with vertex attribute. So you've got this attribute in your shader called color. All right, and then you call GL get attribute location. That's going to return now an integer ID, because OpenGL uses integers for just about everything, and that you're now going to use for anything else that uses this attribute. However, there's a problem with GL get attribute location. Your shader might compile out attributes you're not using. So let's say you've got this attribute for color, but then you're having a problem with your shader and you want to debug it, so you comment out the part that uses color. Or maybe you don't just comment it out. Maybe you just, before you use color, just kind of put a return in your function. The compiler is really awesome and detects that and optimizes it all out and sees that color's not used and throws it away, and then you go get GL attribute location. It says, what? I have no idea what that is. I optimized that out. I forgot everything I saw about your program when I first loaded it up. All I know is the actual optimized version. So now you've got all this code that's maybe getting attribute location or doing error checking, and you comment out one line of code. Now your error checking is saying goofy things are going on. It's really annoying. It is a huge source of confusion. When I help people with their CS300 assignments, this is one of the things that I see people get really confused on. Yeah, so it's a bad function. And the best part is that there's absolutely no ever call it. Why people do not use it. If you see people using it, tell them not to use it. And if you find something online that says to use it, stop reading that site and go read a different site. There's another function called GL bind attribute location. You call this one before you call GL link. In this case, you're saying, hey, OpenGL, I've got this attribute called color. I'm going to tell you the integer name I want to use. I want color to be ID 1 for attributes. And then it just sets it to 1. And if it gets optimized out, it doesn't care. So you call these functions for all, spell it right though, location, not location. Yeah, call it beforehand, and then all those problems of GL attribute location, get attribute location just disappear, and you are much happier and will hate OpenGL slightly less. And then getting on to really modern stuff, in newer versions of GLSL, they have added a way for the shader to specify the integer ID, which is actually a lot like how HLSL from Direct3D works. In Direct3D, you specify an attribute and you say, this is the color attribute, where color just kind of maps internally to an integer in Direct3D. In OpenGL, they don't have the nice names for it, but inside of your shader, you can add this layout location equal stuff. And now the shader, when it compiles it, will just set it automatically. So you don't have to split your shader between your shader code and your C++ code. It's all kind of localized in one place. It's really great. But it requires OpenGL 3.3 or higher for this feature unless you have access to one of the extensions, but they're iffy support. And there's a problem with that, and that problem's name is Intel. So yeah, you actually can't really use this in a lot of cases if you want to support a wide range of hardware, including a lot of laptops that people here at DigiPen are using. But still, it's a cool thing. Give it a few years. This will probably be something you can actually use in real OpenGL. Oops, real OpenGL games. Uniforms. Uniforms are where an attribute is per vertex. So if you have a model, you set this attribute for each vertex in the model. A uniform is a global or a constant that exists for the entire model. So you have like one value instead of one for each vertex. And again, there's a couple different ways to set these. The original version is a lot like GL get attribute location. There is no GL bind uniform. little annoying, but otherwise it's similar to the way GL vertex works. Once you have the name for a uniform, you call GL uniform, and say you want to set one float, we do GL uniform 1F, and then what you want to set. Yeah, not much to that. There's also what's called a uniform buffer. This is kind of an advanced thing. If you hear of constant buffers in Direct3D, that is the OpenGL equivalent. It is a pain in the butt in OpenGL. To use them, the API they invented is not surprisingly really bad. The shading language support is a little wonky compared to HLSL, and it's only in OpenGL 3.1 plus. And again, thanks to Intel, there are tons of people running hardware that is fully capable of running Direct3D 10 and OpenGL 3.3, but the drivers only support OpenGL 3.0, and they don't have this feature, and that is a problem. And then let's see, one of the other big features you're going to want to use for advanced techniques is called a frame buffer object. If you're doing post-processing, which you do for like a lot of really cool effects, especially 2D effects, most of the ones you use are going to end up being a form of post-processing. You need to use a frame buffer object. And I want to go over these because, again, there's some wonkiness of the API you should be aware of and that the online sources do not go over very well. So a frame buffer object is a texture you can render into. So instead of rendering to the screen, you render to some other chunk of memory that you can then use as a source for rendering something else. So if you want to like render into a picture that you then render into a little corner in your scene, that's how you do that. All right, so this is a bit more traditional. You have an integer name, gem frame buffers, bind the frame buffer so you can do stuff to it. Straightforward. So now that you've got a frame buffer, you got to give it the texture you want to render into. So you've already created a texture. You got to do that. But you have to give the texture a size. Now, you're not giving the texture data. You're not uploading a texture off file because you're creating it on the GPU. You're rendering into it. But it has to have a width and a height. And the only function that sets width and height is GL text image 2D, which is the one you use for uploading data. So you call it, but you pass null for the data, and that'll make it have a size, but not have data, essentially. So you have to remember to call that. And then you can attach the texture to the frame buffer using a function like that. Not much to it. Just so you know, the GL color attachment 0, you can have GL color attachment 0 plus 1. There's not actually a GL color attachment 1 in the standard headers, so you just add 1 to it. But that's so you can have multiple texture support. You need that for a few advanced features that you would do in 3D sometimes. You probably won't need it for anything 2D. Then there's a thing called a render buffer. A render buffer is another one of those great features that they thought would be the way hardware would work in the future, and it kind of isn't. The idea of a render buffer is that they are faster than textures, and they're faster because you can't use them for anything. Basically, you can use them for depth buffers and nothing else. In theory, they can be faster. I don't think they actually are, but it's considered good practice to use them. So you'd call GL gen render buffers, you get a render buffer, bind it, attach, oh yeah, storage. So you got to tell it what format you want it in. Because it's not a texture, you can't use GL text image 2D. Your old trusty friend, they have yet another new function for you. So you got to give it a width and height. Very, very important. Your width and height for your depth buffer must be the exact same as the texture you're rendering into. If you have a 1000 by 1000 texture you're rendering into, you have to have a 1000 by 1000 depth buffer if you're using a depth buffer. If you're not using depth testing, you don't need this at all. But if they are different, it will not work. You will get errors, and yeah, you're going to be in trouble. Other thing is this line here, the GL depth stencil 24.8. Stencil buffers are another type of buffer. They're usually kind of combined with depth buffers. You might not be using them, but this is always the safest one to use because this one is guaranteed to be hardware implemented in every implementation. Whereas other ones that you might think are faster because you're saving space, because they're not hardware accelerated, it's actually slower. So just always use that one, essentially. You also need to attach the render buffer. I apparently didn't put that in the slide, but just like you called GL frame buffer texture 2D, there's one for GL frame buffer render buffer. And you call that your render buffer. Now when you want to render into your texture, you call GL bind frame buffer before rendering. Now anything you render goes into that texture. If you call GL clear, it will clear that texture. And then when you want to now render back to the actual screen itself, you just call bind frame buffer 0. So one of the things now is frame buffers are a source of confusion and errors. There's a way to check if your frame buffer is correct. You call GL check frame buffer status, and it will return a value. If it returns GL frame buffer complete, it's good. If it returns anything else, it won't tell you what's wrong, but something is wrong. It is totally not helpful. but I will bet you $1 it's your sizes are not correct or you forgot to bind a color buffer. So if you're getting errors with your GL check framework for status, double check texture sizes. That is by far the most common mistake. All right, so I'm going to go over a little bit about OpenGL versus Direct3D, why you might choose OpenGL, why you might choose Direct3D. I'm then going to rant a bit more about OpenGL, if that theme has not become apparent yet. All right, so OpenGL versus Direct3D. So Direct3D is a lot easier for medium to difficult graphics kind of stuff. The OpenGL API, again, all those extra functions you call the binding, the error checking is weak. Getting up and running, very easy. Doing anything advanced, you will start running into lots of errors. It'll be difficult to find out why. Direct3D's API just makes those advanced features easier. The downside is, however, that just for simple stuff, Direct3D requires you to call like a bunch of setup functions. You're going to pass in a ton of state. It's a lot of cut and paste code. It's not a huge deal, but if you're just sitting down and want to write something right away, OpenGL is easier in that case, and not really in other cases. The Direct3D drivers on Windows are a lot better. You're going to run less bugs. You're going to have better performance in general. But that's something that's only for Windows, because on other platforms you don't have Direct3D. The Direct3D has better tools, and Pix is really great. NVIDIA has some Direct3D only tools and a couple tools that can do OpenGL, but does it poorly. And then this is kind of more of an opinion one, but I find HLSL to be a nicer language than GLSL. They are slowly fixing GLSL, but it's the thing like only the version in GLSL that comes with OpenGL 4.2 adds some really necessary for convenience features. And you can't use OpenGL 4.2 because almost no one has a graphics card that can actually run it, because that's Direct3D 11 quality hardware, essentially. However, on OpenGL side, it's got one really huge advantage for it. It runs on lots of platforms, including the mobile platforms, and because of the mobile platforms, there are way more jobs right now for OpenGL programmers than Direct3D programmers. And because also for indie games, it's really important to hit multiple platforms. Right? If you're a big studio, maybe you can ignore OS X users because there's not that many of them. But if you're an indie, you're a small indie game, every single sale you get can count. So the more platforms you can hit, the more money you're going to make, and the better chance you have of actually being profitable and successful. So OpenGL can be a really strong choice just because of its portability. Technical issues completely aside, it is a useful thing to know. And if you're worried about getting a job, I'm going to hate to break it to you, but the odds of being like on a AAA major ultimate shooter are a lot lower than you getting a job with mobile games, and mobile games are OpenGL. So it is a good API to have familiarity with. OpenGL does have a lot of problems. The error reporting, debuggability is not good. The API is not thread safe. The way that you have to like bind something and then call another function, when you get into threads, that's really bad, because now you bind something and then another thread needs to modify something it wants to bind something, but there's no way to synchronize this unless you have locks, and it's just a real pain. And actually on some OSs, it's actually just outright impossible to use starting with OpenGL, which is really unfortunate. The API is error prone, and the one thing that really annoys me is that on Windows with the standard OpenGL headers, it confuses IntelliSense. So you type in the name of an OpenGL function and you're expecting it to pop up and tell you what the arguments are because, come on, it's 2012. It won't. Just the way that the Windows version of OpenGL works, the way the headers are defined, it confuses IntelliSense. It works okay on Linux and OS X, but most of you guys will be working on Linux or Windows, so that's just something to be. With Direct3D's problems, you can't use it on Windows and Xbox. Yep. I don't know. Some people hate Direct3D because they hate Microsoft. I was a Linux guy for 10 years, so I was also once an anti-Microsoft bigot before I saw the light. And some people just hate Microsoft, and hence OpenGL is all that matters because it's not Microsoft. That's the best reason to make decisions. But, so a little list of OpenGL complaints, and I think I've ragged enough on OpenGL at this point, but again, if you're using it, we have some very high energy personalities here at DigiPen who despise OpenGL with a burning passion, and they're going to say things, and I want to make sure you are equipped to nod at them and say you are correct. Here's why I know you're correct, and here are reasons. I'm going to use OpenGL anyway because I got my reasons, but this kind of helps you start running into issues to realize that it's not your fault. You're not stupid. OpenGL is stupid. So one thing is OpenGL uses those integer identifiers for everything. So textures was an integer ID, your shader was an integer ID. This means that your functions that modify textures, that just take an integer, you can accidentally pass a shader ID into them. That kind of sucks. And again, IntelliSense won't help you. You're going to type, even if IntelliSense worked on the Windows ones, it's going to pop up and say integer. What? I've got like 20 different OpenGL objects. Which one am I supposed to pass into you? I have no idea. So it's error prone, and it has bad tool support. And then, IntelliSense. There's really weak error reporting in OpenGL. Basically, things will fail, and there's a function to get the error status out of OpenGL. It will almost always return GL invalid operation. You don't know what the operation, why it was invalid. And because of the multiple function calls you have to make to do anything, it actually might have been the first function calls when you screwed up, but it doesn't actually notice the error until 3 function calls later, and then you get invalid operation. It's really hard to find out. If you did something wrong, it is really hard to find out what you did wrong sometimes with OpenGL. There are tools like GDebugger, which help. You should always be using programmers' tools are like what your bread and butter, Visual Studio, things like that. GDebugger is the tool you use for OpenGL. I want to point out there are 2 major versions of GDebugger. There is the original version made by Gremedy. If you search for GDebugger, you're going to get their site. The problem is that they stopped updating GDebugger years ago. AMD bought it, and AMD now maintains it, but they don't use the old site. They have their own site on AMD's website for GDebugger. But if you Google GDebugger, you're going to end up at the old site. You're going to download an old, crappy, buggy version that doesn't support newer features. So make sure when you go to download GDebugger, you get it from AMD's site and get the newest version. It's a lot better than the older version. All right, so another issue that you might see if you get online, you're going to hear the mutable thing come up a lot when people talk about OpenGL. That means you can modify objects after you've created them in ways that don't make sense. Like you can create a texture and then resize the texture. This is not the hardware can't actually do that. Hardware cannot resize textures, so you do not want to do that. But the OpenGL API says you have to be able to do that, and the driver has to support it. So if you're writing a driver, you have to do like all this extra work to make sure that the user might be able to try to modify an object, and you've got to deal with these situations that the hardware can't deal with, and the user shouldn't be doing, but the user doesn't know that because OpenGL is saying, yeah, do this, it's supported. And again, so now you're going to think modifying objects is smart. It's not. If you want a new texture, make a new texture. Do not modify the existing texture. I mean, replacing the data in your texture is fine, but don't resize it or think you're saving, saving anything by trying to reuse objects in weird ways. You're not. And then there's the many sequential function calls. This, it's a pain, and again, the error reporting is weak with that. So the API is based on a state machine. That's why you have those global function calls and the bind functions. It's really awkward. It was a good idea maybe in the late 1980s and when they released it in the early 90s, but today we would like a really nice object-oriented API, which means we want Direct3D. But OpenGL has what it has there. So OpenGL does not provide a lot of helper functions. I went over before, things like loading a texture. You've got to use a third-party library for that. Whereas Direct3D's utility library kind of does a lot of that for you, even as like model loading and like an effects framework for shaders. It's kind of cool. OpenGL gives you nothing. The OpenGL utility library is math functions. And these are like functions that once you take CS250, you can write yourself in 5 minutes. They're not that huge of a utility. I mean, they're nice to have. I'd rather have them than not have them, but not enough utility. The threading is impossible, which is an issue for high-end rendering. If you're on a AAA game, you're going to care about that. If you're not on a AAA game, you actually don't really care about that. But, and then there's the deprecation model. So there's all these old functions in OpenGL that you should not use because they're silly. They don't represent the way hardware actually works. But they never get rid of anything. They did that one deprecation model, the core profile I mentioned for OpenGL 3, where they got rid of a bunch of old functions, and then they've pretty much said that they're not going to ever deprecate anything again. So in a few years, the core profile will still be filled with tons of compatibility, deprecated stuff that they'll never get rid of. Oh, yeah, my favorite. So the drivers are crap because they're slow. The OpenGL drivers are crap because they're buggy. They're crap because they only support old GL versions, and again, Intel is just awful. Just so awful when it comes to their OpenGL drivers. They just released for Ivy Bridge GPUs finally a driver that can actually do OpenGL 3.3 and I think even OpenGL 4.0, which is amazing. I mean, their previous generation of hardware that was capable of Direct3D 10, which means anything in the OpenGL 3 version would only support OpenGL 3.1. They don't update their old drivers, so if you've got older hardware that's not Ivy Bridge that can do hardware features, you're still not going to be able to access those features with OpenGL with Intel. This is the complete opposite from AMD and NVIDIA, where again, they use extensions in OpenGL and they expose features to OpenGL before Direct3D comes out the new version and gets those features. But yeah, Intel is the most common graphics card in the world. I mean, most people don't buy discrete GPUs, especially on laptops these days anymore, outside of gamers. So not being able to support Intel is a huge problem, which is why if you're going to be doing OpenGL on PC, targeting a wide base of users, you're going to be using OpenGL 2 and avoiding a lot of the really cool features that it'd be really nice if you could use. That alone is just the single biggest, most depressing thing about OpenGL is the fact that they're... All right, so summary, if you're just targeting a PC, there's a strong use case to just use Direct3D. Again, if you're doing anything besides just little simple stuff, it's a nicer API. If you're targeting mobile, you are using OpenGL ES. I mean, yeah, sure, the Windows mobile platform is using Direct3D, but I think Windows Phone is at like less than 1% market share still. iOS and Android are where all the action is at, and they are OpenGL ES. And again, that is a huge segment of the games market right now. Most of you will probably end up with jobs doing mobile games, at least especially right out of college, if not, as your entire career. So if you're going to be doing graphics programming, you are probably going to be doing it in OpenGL, like it or not. The big AAA engines, you might think, yeah, okay, Direct3D, that's better for the bigger stuff, except even the bigger AAA engines now run on mobile platforms. OS X is becoming a viable gaming market. There's even rumors that Linux will somehow magically become a viable gaming market soon. So OpenGL is something that you still have to support even in a AAA game engine. So there, it's not like, well, Direct3D is easier and that makes it easier to write our engine. The reality is that you're actually just abstracting away, so your graphics programmer in your engine is actually using some internal engine API, and then it's just this thin layer that basically hides away the Direct3D versus OpenGL. It's going to be a lot easier to write the Direct3D wrapper, because OpenGL 1 is going to be a pain in the butt, but you're going to have to do that. So, and then consoles don't use Direct3D or OpenGL. Xbox uses Direct3D, but on the Sony PlayStation, there is in theory an OpenGL library. No games actually use it. They all use the custom Sony API. The same with the Wii, 3DS, and all that. They're using custom APIs. So yeah, there's no one API that you can just go, this is the best one and the only one I will ever use, if you plan on doing a lot of platform support. Some other resources for you. I have collected a few links that are actually decent, because if you Google OpenGL help, you're going to get a lot of links that were written 10 years ago or were written by people who have no idea what they're talking about and should not be allowed on the internet. This first tutorial here is a fairly good one. It's modern OpenGL. The guy that writes it is really smart. He's actually really active in the OpenGL community. He really knows what's going on. It's a good tutorial. It only goes over the modern OpenGL stuff. So not the OpenGL 1 like I went over. It's all OpenGL 3 and the good stuff. The OpenGL boards can be a good place to get help. There are some interesting characters on that forum to be aware of, but they are smart, interesting characters that can help out with like really wonky issues sometimes. Game Dev Stack Exchange. Stack Exchange in general is one of the most important sites you can ever go to for help. It is, for those who don't know, it is a site where you ask a question and people give you answers. And if you go to the programming-related Stack Exchanges, there's a lot of very smart people that will give, it's like crowdsourcing answers. So you're basically asking the internet for help, and it's a place where smart people collect and answer your questions. It's really useful. The game dev subboard is a good place for getting anything graphics related or game related in general. And there's also a couple others where graphics questions are posted as well. OpenGL book I like a lot. Unfortunately, it's incomplete, but I'm going to point this to you guys just in the hopes that you will go to it and go, this is really well written and awesome, and then you pester the author to write some more chapters. Because it's one of the best written tutorials I've seen on OpenGL, but he's only gotten up through 4 chapters, so it's basically just getting some basic stuff on screen, like a textured color triangle, and it stops there. But I mean, it's really well written. The code samples are great. It's a good one. If you're more interested in, instead of my examples, you want something that's very code heavy, this is a good one to go to. And then GameDev.net, their forums are okay. It's been kind of dying off lately. A lot less activity these days, but there are, again, some smart people there that actually know what they're talking about. So if you're going to do forum-based help, it's a good one to have. So you notice there's actually only 2 links on here that are just links to tutorials. There's a reason for that. OpenGL tutorials in general suck. These are the ones to use. Don't use any others. The Nihi tutorials are really popular. They are really outdated. Do not use those, for the love of God. Do not go to those. Do not do anything with those. If you're looking for printed resources, there are a few good ones. The OpenGL Super Bible is like the really popular one. I mean, it's okay. It's a book. It won't lead you astray. The OpenGL ES2 programming guide is a good one if you're going to do mobile programming, iOS stuff. It's a pretty standard book. Game Engine Architecture is a popular book. A lot of people in DigiPen right now are raving about this book. It's got some graphic stuff in there, and it'll get you some basics. It's a good book to read through. Then the OpenGL Programming Guide is like the official reference. So it's not a tutorial. It's mostly just a big book full of all the stuff OpenGL has and does. I will note that 5th edition, 8th edition, this really matters because again, there's a lot of versions of OpenGL. So if you get an older edition, it's not going to cover the newer stuff, or it might give you not as good advice based on what modern hardware does. And obviously, within like a year, these slides will be out of date, and you should be looking probably at 6th edition and 9th edition, or whatever the newest version. Just check the year. Make sure it's within a year or 2 of the published date whenever you buy one of these books. Standard programming stuff. Graphics does actually change very rapidly in the computer industry, so it matters which version you get. And that was my brief little filler presentation. So if you guys have any questions about the presentation, feel free to ask. If you have any interesting how do I do something question, you can ask me. I'm not a graphics programmer, but we've got a few people in the club who know stuff about graphics. Unfortunately, a couple of them that are usually here at Graphics Guys I don't see today. So next week might be a better week for some of the really advanced stuff. But yeah, there's people here that can answer pretty much any question you have about graphics. So if you're stuck or just curious, ask.